A journey to the edge of the universe. We live in an unimaginably vast universe, filled with trillions of galaxies, each containing hundreds of billions of stars. Despite its enormity, tools like the Hubble and James Webb space telescopes have allowed us to map billions of these galaxies and peer into the farthest reaches of the cosmos. Today, we'll embark on the ultimate voyage through space and time, traveling beyond our galaxy to explore the most awe-inspiring and significant landmarks along the way. The Observable Universe. Before starting this cosmic journey, it's essential to understand the edge of the universe. What we often call the Observable Universe or the Hubble volume is a spherical region of space surrounding Earth, containing everything we can see because their light has had time to reach us. Light, traveling at nearly 300,000 kilometers per second, moves fast on earthly scales but incredibly slow over cosmic distances. As a result, objects farther away appear as they were billions of years ago. The universe is 13.8 billion years old, meaning the farthest light we can observe comes from galaxies whose light traveled 13.8 billion years to reach us. This makes the edge of the universe as much a time barrier as a spatial one. As we look farther, we also look back in time. Telescopes like James Webb function as time machines, peering into the universe's early stages. They capture light that has been stretched and reddened by the expansion of space, a phenomenon known as redshift. Redshift provides astronomers with a scale, denoted as Z, to measure distances, serving as our guide on this journey. The local volume. Our journey begins on Earth, a mere speck in the vast universe. Even within the solar system, our significance is dwarfed by the immense scales of space. Our galaxy, the Milky Way, is just one of at least 100 billion galaxies. The Milky Way belongs to the local group, a small cluster of over 30 galaxies spread across 10 million light-years. The local group includes three significant members: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. These galaxies are gravitationally bound and on a slow collision course. Beyond this, we encounter the local volume, spanning 30 million light-years and containing over 500 galaxies, including fascinating formations like the Council of Giants and starburst galaxies like NGC 253. ### Virgo Supercluster and Laniakea. Traveling further, we reach the Virgo cluster, 65 million light-years away, home to over 1,500 galaxies, including Messier 87, an elliptical galaxy with a supermassive black hole famously imaged in 2019. The Virgo cluster is part of the Virgo supercluster, a vast structure of thousands of galaxies extending over 100 million light-years. Even larger, the Laniakea supercluster encompasses the Virgo supercluster and over 100,000 galaxies across 500 million light-years. Laniakea's gravitational flows point toward the Great Attractor, a mysterious mass region partially obscured by the Milky Way. Recent surveys reveal its influence stems from the Norma cluster, Hydra Centaurus supercluster, and even more distant structures like the Shapley supercluster and Vela supercluster. The Sloan Great Wall and galaxy filaments. At 1 billion light-years, we encounter the Sloan Great Wall, a massive galaxy filament spanning 1.3 billion light-years. It's a dense formation of galaxies and superclusters, though debates continue over whether it's a single structure or an alignment of several. Filaments like the Sloan Great Wall are the largest structures in the universe, connecting galaxies along the cosmic web. These threads of matter guide the evolution of the universe, serving as scaffolding for galaxy clusters. Active galactic nuclei and quasars. Beyond 1.5 billion light-years, we begin to see a younger universe, filled with galaxies undergoing collisions and rapid evolution. These interactions feed central supermassive black holes, creating active galactic nuclei (AGN), some of the brightest objects in the universe. Radio galaxies like Alcyonius, with emissions extending over 16 million light-years, showcase these energetic processes. Among the most luminous AGN are quasars, driven by superheated accretion disks around black holes. Quasars shine so brightly they outshine their host galaxies and can be seen billions of light-years away. The iconic Quasar 3C273, 2.5 billion light-years from Earth, was the first identified, marking the discovery of a class of objects that illuminate the distant universe. The Deep Universe and Quasar Epoch. As we venture beyond 8 billion light-years, redshift z equals 1, quasars become increasingly common, marking a period known as the peak quasar epoch, around 10 billion years ago. These quasars help map the galaxy filaments of the early universe, acting like luminous beacons against the cosmic void. In this ancient universe, smaller black holes spaghettified gas more efficiently, creating more quasars than we see today. They highlight the dynamic, chaotic processes that shaped galaxies in the early cosmos. The edge of the universe. The farther we travel, the closer we get to the universe's birth. Beyond 13 billion light-years, galaxies and quasars give way to the cosmic microwave background, CMB, the faint glow of the Big Bang. This light, stretched to microwaves by the universe's expansion, represents the true edge of the observable universe and the beginning of time as we know it. This journey through the universe showcases not just its immense scale but also its incredible history, from chaotic beginnings to its structured present. As telescopes improve, our understanding of the cosmos will continue to grow, revealing even more about the universe's mysteries. ####Large quasar groups and cosmic structures. Large quasar groups, LQGs, are clusters of quasars spanning multi-billion light-year distances. While they're not gravitationally bound, their sheer scale ranks them among the largest known structures in the universe. At a distance of 8.8 billion light-years from Earth lies U1.11, a quasar group with 38 quasars spread over 2.2 billion light-years. Neighboring it at redshift 1.28 is the Claus-Campusano LQG, comprising 34 quasars over a similar expanse. The largest of these, the huge LQG, consists of 73 quasars, stretching over 4 billion light-years at redshift 1.25. Although these formations might result from random alignments rather than actual structures, they remain significant in our list of cosmic marvels. The largest structure, Hercules-Corona Borealis Great Wall. Surpassing LQGs, the largest known structure isn't composed of quasars but a gamma-ray burst, GRB, formation. GRBs are immense electromagnetic explosions, releasing energy equivalent to a star's entire life cycle in mere seconds. These bursts result from phenomena like supernovae or neutron star mergers. At redshift 1.6, scientists identified an aggregation of GRBs forming the Hercules-Corona Borealis Great Wall, spanning an extraordinary 10 billion light-years. Despite being termed a wall, it likely results from random spatial distributions rather than an actual filamentary structure. Cosmic high noon. At redshift 2, about 11.18 billion light-years away, we reach cosmic high noon, a period roughly 2.6 billion years after the Big Bang when star formation peaked. Young galaxies during this era formed stars at rates thousands of times greater than our Milky Way's current rate. This era also features hot dust-obscured galaxies, hot dogs, luminous quasar galaxies shrouded in dense gas. NASA's WISE telescope identified over 1,000 hot dogs between redshifts 2 and 4, corresponding to look-back times near 13 billion years. The redshift barrier. As we observe galaxies beyond redshift 3, their emissions are increasingly faint due to the universe's expansion. At such distances, galaxies appear to recede faster than light due to the stretching of space. This doesn't violate physics, as it's the space itself that's expanding. Modern observatories like the James Webb Telescope help probe these faint emissions, revealing primordial galaxies from the universe's early epochs. Epoch of reionization. This period followed the emergence of the first stars, population 3 stars, formed from the primordial gas of the Big Bang. Their intense radiation reionized the universe's neutral hydrogen, stripping electrons and converting the gas back into plasma. This reionization phase, lasting around 150 million years, ended at redshift 6. Astronomers debate whether this process was driven by numerous small galaxies or a few massive oligarch galaxies. Farthest known galaxies. In recent years, astronomers have identified galaxies at staggering depths. GN is E11, at redshift 11.1, this galaxy formed 420 million years after the Big Bang. HD1, estimated at redshift 13.27, it likely emerged just 330 million years after the universe began. Class Z13, discovered by James Webb, it lies at redshift 13, around 13.5 billion light-years away. Due to cosmic expansion, these galaxies are now estimated to be over 33 billion light-years from Earth. The universe's dark age. Beyond redshift 20 at 13.6 billion light-years, lies the dark age, a time before light-emitting stars existed. The universe was dark and filled with neutral gas, awaiting the cosmic dawn when the first stars ignited. The cosmic microwave background. The oldest detectable light, emitted 379,000 years after the Big Bang, is the cosmic microwave background, CMB. Initially optical, this light has been stretched into the microwave spectrum due to the universe's expansion. The CMB marks the edge of the observable universe, spanning a radius of 46.5 billion light-years. However, this is not the actual edge of the universe, as much lies beyond the cosmic event horizon, hidden from our view. Beyond the observable universe. The observable universe is limited by light's travel time and our position in space. Scientists believe the universe extends far beyond our cosmic horizon, but the extent and nature of what lies beyond remain unknown. Future exploration may provide insights into these hidden regions.